So here we have a procedure that we can use to graph polynomial functions. To graph a polynomial function, 1. Use the leading term test to determine the end behavior. 2. Find the zeros of the function by solving f of x equals 0. Any real zeros are the first coordinates of the x-intercepts. 3. Use the x-intercepts, or the zeros, to divide the axis into intervals and choose a test point in each interval to determine the sign of all function values in that interval. 4th, find f of 0. This gives the y-intercept of the function. 5, if necessary, find additional function values to determine the general shape of the graph and then draw the graph. And 6, as a partial check, we can use the fact that the graph has at most n x-intercepts and at most n minus 1 turning points. Multiplicity of zeros can also be considered in order to check where the graph crosses or is tangent to the x-axis. We can also check the graph with a graphing calculator. So let's look at an example. So in this example, we want to graph the polynomial function g of x equals -1/2 times the quantity x plus 3 times the quantity x minus 1 squared times the quantity x plus 1. And so we're going to use our 6-step procedure to do this. So we want to begin by thinking about the end behavior. So to determine the end behavior, we need to determine the degree of the polynomial function and the leading coefficient. So in this particular case, if we were to multiply out this polynomial function here, so instead of having it in factored form, if we were to multiply it out, we would get a factor of x when we multiply it out from this first factor, x plus 3. We would get 2 factors of x from the x minus 1 squared, and we would get another factor of x from the x plus 1. So we would have x times x squared times x, which would be x to the 4th. So we would have an x to the 4th term, and the coefficient of that would be -1/2. So in other words, if we were to multiply this all out, we would get -1/2 times x to the 4th power, and then plus more. But this would be the leading term. So our leading term has a degree of 4, and we have a leading coefficient of -1/2. So we have an even degree, and we have a negative leading coefficient. So the fact that we have an even degree means it's either going to be up, up, or down, down. And the fact that we have a negative leading coefficient means that the end behavior is going to be down, down. So it's going to head down on the left and down on the right. So our second step, we want to find the zeros and their multiplicity. So to find the zeros of our function, we're going to take -1/2 times x plus 3 times x minus 1 squared times x plus 1 and set it equal to 0. So this means that -1/2 equals 0, which of course is ridiculous. -1/2 does not equal 0, so we can disregard that. Or x plus 3 equals 0, or x minus 1 equals 0, and we would actually get that twice, or x plus 1 equals 0. Now, if x plus 3 equals 0, that means x equals -3. If x minus 1 equals 0, that means x equals 1. And if x plus 1 equals 0, then that means x equals -1. Okay? Now, again, we had one factor of x plus 3, so we have the 0 of -3, which has a multiplicity of 1. We had 2 factors of x minus 1, which means that the 0, x equals 1, has a multiplicity of 2. And we have only one factor of x plus 1, which means -1 has a multiplicity of 1. So our zeros are -3, 1, and -1. -3 has a multiplicity of 1. 1 has a multiplicity of 2. And -1 has a multiplicity of 1. So step 3, we want to complete our table of signs. So to do this, we're going to consider our 3 zeros, which were -3, -1, and +1, and I've just put those in order. Recall that -3 had a multiplicity of 1, -1 had a multiplicity of 1, and +1 had a multiplicity of 2. So these 3 zeros divide the number line into 4 intervals. So we're going to look at the interval from -infinity to -3. We're going to look at the interval from -3 to -1, at the interval from -1 to +1, and then from the interval from 1 to infinity. And so we're going to use this to create a table of signs. So what we're going to do is we're going to select a value from each interval, substitute it into our function to see if we get a negative or a positive value. Now remember, our function is g of x equals -1/2 times x plus 3 times x minus 1 squared times x plus 1. And just for reference, I'm going to rewrite that here. So g of x equals -1/2 times x plus 3 times x minus 1 squared times x plus 1. Okay? So we're going to choose a test value from our first interval here. So that can be anything between -infinity and -3. So for example, -4 would be a good test value. And so we're going to find g of -4. So I'll do that down here. G of -4 is going to be -1/2 times -4 plus 3, substituting -4 in for x, times -4 minus 1 squared times -4 plus 1. Again, substituting -4 for x. So that's going to give us -1/2 times -4 plus 3 is -1. -4 minus 1 would be -5. Squared would be +25. And -4 plus 1 will be -3. So we have -1/2 times -1, which is +1/2. +1/2 times 25 would be 25 halves, and 25 halves times -3 will be -75 halves. So when we find g of -4, we get -75 halves. Now the truth is, the specific value doesn't really matter to us so much as the sign of the value. So this gave us a negative value, okay? So that means that the portion of the graph is going to be below the x-axis when we're on the interval from -infinity to -3. So when we graph this, the graph is going to be below the x-axis whenever we are to the left of -3. So the location of points on the graph is going to be below the x-axis. Now let's do the same thing for our other 3 intervals. So between -3 and -1, we can choose a test value. -2 would be a good test value. So we want to find g of -2, and really, in particular, what we want is the sign of g of -2. So g of -2 is going to equal -1/2 times -2 plus 3 times -2 minus 1 squared times -2 plus 1. Again, just substituting -2 for x in our function. So that is going to be -1/2 times -2 plus 3 is 1. -2 minus 1 is -3 squared. That is -3, and we're squaring it. That's going to give us 9. And -2 plus 1 is -1. So -1/2 times 1 is -1/2. -1/2 times 9 is -9 halves. -9 halves times -1 is +9 9/2. So g of negative 2 is positive 9/2. So the sign is positive, which means our graph on that interval will be above the x-axis. So when I am between, say if here's negative 3 and here's negative 1, we're going to be above the x-axis in that area. Negative 1 to positive 1. On that interval, we can choose a test value, again, which means any number between negative 1 and positive 1. So 0 would be a nice test value. So we need to find g of 0. Well, g of 0 is going to equal negative 1/2 times 0 plus 3 times 0 minus 1 squared times 0 plus 1. So that's going to be negative 1/2 times 0 plus 3 is 3. 0 minus 1 is negative 1. Squared is positive 1. And 0 plus 1 is 1. So we have negative 1/2 times 3, which is negative 3/2, times 1, which is still negative 3/2, times 1 again, which is still negative 3/2. So g of 0 is negative 3/2. The sign is negative, which means on this interval we are below the x-axis. Last but not least, we need to choose a test value from 1 to infinity. So again, we can pick any number larger than 1. Let's pick, how about 3? So if we find g of 3, that's going to be negative 1/2 times 3 plus 3 times 3 minus 1 squared times 3 plus 1. So that's going to be negative 1/2 times 3 plus 3 is 6. 3 minus 1 is 2. Squared is 4. And 3 plus 1 is 4. So we have negative 1/2 times 6, which is negative 3. Negative 3 times 4 is negative 12. And negative 12 times 4 is negative 48. So g of 3 is negative 48. And the sign of that is negative. So again, for this interval, we're going to be below the x-axis. So at positive 1, between negative 1 and positive 1, we're going to be below the x-axis, and to the right of positive 1, we're still going to be below the x-axis. So step 4, we want to find the y-intercept. So to find the y-intercept, we're going to find g of 0, and we actually did that in step 3. In step 3, we found that g of 0 was equal to negative 3/2. So our y-intercept is the point 0, negative 3/2. Now we want to make a rough sketch of this graph. So summarizing what we found, we know the end behavior is going to be down, down, down on the left, down on the right. We know that the zeros are negative 3, negative 1. Both of those have multiplicity of 1. And positive 1, that has a multiplicity of 2. So that means we have x-intercepts at negative 3, at negative 1, and at positive 1. So if here's negative 1, negative 2, negative 3. And if here's 1, 2, 3 on our graph. So we're going to have an x-intercept at the point negative 3, 0. We're going to have an x-intercept at negative 1, 0. And we have an x-intercept at 1, 0. Again, because those were the zeros. We know that negative 3 and negative 1 had multiplicity of 1, which means our graphs should cross the x-axis at those intercepts. We know that 1 has a multiplicity of 2, which is even, which means our graph should only touch there. In other words, our graph should be tangent to the x-axis at the point 1, 0. We have learned from step 3 that when we are in the interval negative infinity to negative 3, our graph is going to be below the x-axis. So our graph is going to be below the x-axis when we are to the left of negative 3. And then when we are in between -3 and -1, our graph should be above the x-axis. When we are between -1 and 1, we should be below the x-axis, and then when we're to the right of 1, we should again be below the x-axis. So again, if we are above the x-axis between -3 and 1, that means our graph is going to have to come up and somehow stay above, but it's got to come back down and cross here at -1. Now we also know we have a y-intercept at 0, -3/2. So like if here is -1 and if here is -2, then -3/2 would be here. We have a y-intercept. So we've got to come down and cross at the y-intercept. Okay, we have to come back up in order to have this x-intercept, but we have to stay below the x-axis when we're to the right. So this is going to come back up, touch, and then come back down in order to be below the x-axis on the interval from -1 to 1 and to remain below the x-axis on the interval from 1 to infinity. And again, we're tangent at this point, which is an indicator from the fact that we have a multiplicity of 2. So this is a rough sketch of what our graph should look like. Now we can check that by graphing it on a graphing calculator. So if I bring in my graphing calculator, I've already typed the equation into the calculator. I'm going to try zoom 6 to see if that gives me a decent picture, and it does. So I can see this verifies what we had analyzed from the function. We do have x-intercepts at -3, at -1, and at 1. The graph is below the x-axis when we're to the left of -3. It is above the x-axis when we're between -3 and -1. We're below the x-axis between -1 and +1, and we are below the x-axis when we're to the right of 1. Again, indicating that the graph is tangent to the x-axis at the point 1, 0, as we already knew. So our graph checks.